Good morning, everyone. Myself, Dr. Pothanna, Associate Professor in the Department of Mathematics and Management Sciences, VNR JYOTHI Institute of Engineering and Technology, Hyderabad. This class, I am going to explain about how to find the solutions of non-exact differential equations using method 3 and method 4. In my previous two lectures, I have explained about how to find the solution of the exact differential equation and what is the condition for exactness and what is the general solution of the exact differential equation. In the second lecture, I have discussed about what is a non-exact differential equation, how to find the integrating factors. After that, how to find the solutions of the non-exact differential equations using method 1 and method 2. Just for 2 to 3 minutes, I am going to explain about what is the exact differential equation and how to write the general solution. That is my first lecture I have explained. Again, I will recall that lecture 1 and lecture 2 now. Just for 2 to 3 minutes, we will discuss that. So, whenever the differential equation mdx plus ndy is equal to 0 is said to be an exact differential equation, we have to check the condition for exactness. That is, whether partial derivative of m with respect to y is same as partial derivative of n with respect to x or not. If the partial derivative of m with respect to y is same as the partial derivative of n with respect to x, then we can say that the given differential equation is exact. Once the differential equation is exact, then we'll write the general solution as integration mdx plus integration ndy is equal to c. We know that in this first integral we'll treat y as constant. In the second integral we take the terms which do not contain x. In the second integral we take the terms which do not contain x. This we know. Okay, to say that the given differential equation is exact, we have to check the condition for exactness, that is dou m by dou y equal to dou n by dou x or not. If it is same, then we can say that the given differential equation is exact differential equation. If it is exact differential equation, then the general solution write as integration mdx plus integration ndy equal to c. In the first integral we treat y as constant. In the second integral we take the terms which do not contain x. In the second lecture, I have discussed about what is the non-exact differential equation. What is the non-exact differential equation? That is, if dou m by dou y not equal to dou n by dou x, then we can say that the given differential equation is non-exact. Then we can say that the given differential equation is non-exact. If the given differential equation is non-exact, before finding the solution, we need to calculate the integrating factors. In the second lecture, I have discussed about how to find the solution of the non-exact differential equations by using method 1 and method 2. Method 1 tells that whenever the differential equation mdx plus ndy equal to 0 is non-exact, and if it is homogeneous, then we'll write the integrating factor as 1 by mx plus ny, where mx plus ny not equal to 0, right? In method 2 we have discussed about whenever this mdx plus ndy in the standard form, some y into function of xy dx plus some x into some other function g of xy dy, okay, that is equal to 0, then we'll write the integrating factor as 1 by mx minus ny, 1 by mx minus ny, where mx minus ny not equal to 0. The given differential equation is non-exact, that is dou m by dou y not equal to dou n by dou x. Then we need to find out the integrating factors. There are many methods are there to find out the integrating factors. In method 1 and method 2, in lecture 2 I have discussed about how to find the integrating factors, then how to find the solution of the non-exact differential equation. In method 1, what we'll see is whenever the differential equation m dx plus n dy equal to 0 is non-exact, and if it is homogeneous, then we'll take the integrating factor as 1 by mx plus ny, where mx plus ny not equal to 0. In method 2, what we'll see is mx plus n dy, m dx plus n dy equal to 0 is non-exact, and which is in the form y of some function of xy dx plus x into g of xy dy equal to 0. So if the non-exact differential equation is there in this form, then we'll take the integrating factor as 1 by mx minus ny, where mx minus ny not equal to 0. In the previous 2 lectures, I have discussed about all these things. What is the exact differential equation and what is the non-exact differential equation, using method 1 and method 2, how to find out the solutions of the non-exact differential equations. This class will see finding the solutions of the non-exact differential equations only, again by using the method 3 and method 4. So in method 3, what we'll see is whenever the differential equation in the form m dx plus n dy equal to 0, and if we able to calculate the partial derivatives dou m by dou y and dou n by dou x, then we can check whether dou m by dou y equal to dou n by dou x or dou m by dou y not equal to dou n by dou x or not. If dou m by dou y not equal to dou n by dou x, then we can say that this is non-exact. In this, we can find some 1 by n dou m by dou y minus dou n by dou x. If you find 1 by n dou m by dou y minus dou n by dou x, so you'll get some expression. No? If we get this expression as some function of x, then we'll write the integrating factor as e to the power of some f of x into dx. In method 3, we'll write the integrating factor as e to the power of integration fx dx. So, but provided this 1 by n, so this difference must be function of x, then only we'll take the integrating factor as e to the power of integration of f of x dx. So here f of x is not integrating factor. Integrating factor is this one, e to the power of integration of f of x dx. This is our method 3. In method 4, we have to check the condition for exactness, and if it is non-exact, that is the differential equation m dx plus n dy equal to 0, then the condition for exactness, that is dou m by dou y not equal to dou n by dou x, means it is a non-exact. It is non-exact. So but if this expression, that is 1 by m dou n by dou x, this difference minus dou m by dou y, if we get this expression as some function of y, then we'll take the integrating factor as e to the power of integration g of y dy. Here this is a function of y, g of y. Here the integrating factor as e to the power of integration g of y dy. So you may ask that, so how can we know whether this 1 by n dou m by dou y minus dou n by dou x is function of x or 1 by m? How we have to decide whether it is a function of x and function of y? Okay, without calculating this, actually we cannot decide that. So what we'll check is whenever the given differential equation is non-exact, okay, to apply the method 3 and method 4. So these are the general methods. So these methods you can apply whether it is homogeneous or maybe in the method 2 form, method 2 standard form, like y into function of xy dx plus x into function of xy dy equal to 0. Okay, that case also you can apply these these two methods here. So the thing is, we have to check these conditions roughly here. So that is whether 1 by n this difference is function of x, or whether 1 by m this difference is function of y or not. Okay, roughly we have to check. If any one of these conditions are satisfied, that means if it is a function of x, then we'll take the integrating factor as e to the power of integration f of x dx. If it is a function of y, then we'll take integrating factor as e to the power of g of y into dy. Roughly we have to check, then only we have to decide that. Now we'll go to one or two problems so that we can understand this, how to apply this method 3 and method 4 here. So let us take one problem here so that we can understand how to solve the given non-exact differential equation by using method 3 or method 4, depends on the condition. So here the question is, solve the differential equation dy by dx is equal to some x square plus y square plus 1 divided by it is 2xy. So this is the first order first degree differential equation. So actually this differential equation is not given directly in the standard form mdx plus ndy equal to 0. So we have to simplify this. After simplification, so you can write this differential equation as x square plus y square plus 1 into dx, then minus 2xy into dy is equal to 0. So after simplification, so we are getting the differential equation, so which is in the form some mdx plus ndy equal to 0. So here m is equal to x square plus y square plus 1 and n is equal to minus 2xy. So after this we have to check the condition for exactness, that is dou m by dou y and dou n by dou x, whether they are equal or not. So dou m by dou y here is, so x terms are constants with respect to y now. So plus derivative of y square with respect to y is 2y, then plus constant derivative is 0. So we got this as dou m by dou y as 2y. And similarly differentiate n partially with respect to x. So here, so minus 2y is the constant, derivative of this x with respect to this x is 1. So that is, so finally we will get this as minus 2y. So therefore dou m by dou y here not equal to dou n by dou x we got. So hence the given differential equation is non-exact. So the given differential equation is non-exact here. So it is actually not a homogeneous. Each and every term in this differential equation, the degrees are not same. And if you want to go to the method 2, that is also not applicable, because it is not not there in that standard form, some y into f of xy dx plus n into g of xy dy. So the alternative is either you can apply the method 3 or method 4, or you can also check whether it is linear or Bernoulli also. Okay, if it is a linear, by using the method of linear differential equation, first order linear differential equation, you can apply it and we can find the solution. And if it is a Bernoulli also, the standard form, if you able to check, so that method also, if it is Bernoulli also, you can apply that. But here I try to find out the solution of this non-exact differential equation by using method 3 or method 4. So before that I want to check whether this 1 by method 3, what we are doing, 1 by n, the difference dou m by dou y minus dou n by dou x. Okay, whether this difference is function of x, then we can apply the method 3 here. So 1 by n here is, so minus 2xy, no, here you can write minus 2xy, and dou m by dou y minus dou n by dou x. So that is dou m by dou y is 2y, then dou n by dou x is minus 2y, this becomes 2y plus 2y. So this is equal to minus 4y divided by 2xy, y gets cancelled. So we got this as minus 2 by x. So this is a function of x, no, this is a function of x. Here we got 1 by n, this difference is function of x. So therefore by using method 3, So this value, this expression roughly we have to check. Okay, initially we don't know whether 1 by n the difference is function of x, or 1 by m the difference, this reverse difference is function of y or not. So one by one we have to check. So here we got 1 by n, this difference as function of x. Then we have to go to the method 3. So method 3, by using method 3, we can write the integrating factor as e to the power of integration f of x dx. So this is equal to e to the power of, so minus 2 by x dx is equal to e to the power of minus 2 integration 1 by x dx. So is equal to e to the power of minus 2 log x. So you can write it as e to the power of log x to the power of minus 2 by using the basic formula log of x power m, you know. Okay, that is m log x or m log n, like that, right? E to the power of some log m base e also we know. Okay, so whenever e to the power of log m base e is there, that is simply m, no? So that is a basic formula. We'll get this as x power minus 2. So you can also write this as 1 by x square. So therefore we got the integrating factor as 1 by x square. Here don't confuse, don't take integrating factor as this one. So it is a to verify that whether it is function of x or any other expression we got or not. To verify that only we have to see this function. So this f of x function, or whatever it may be, the expression will get. Okay, to check that only we will see that. So here the integrating factor is 1 by x square, that is based on e power integration f of x dx. Whatever we'll get, that only will take it as the integrating factor. Once we get the integrating factor, okay, in method 1 and method 2 I have discussed that we have to multiply the integrating factor with the given differential equation to make the differential equation becomes exact. So let us multiply the integrating factor with the given differential equation. The differential equation here is x square plus y square plus 1 dx, okay, minus 2xy into dy equal to 0. This is a given differential equation. After multiplicating this with 1 by x square, so we'll get this as by x square, here also by x square will get. So if you simplify this, you can write this as 1 plus, so x square by x square 1 plus y square plus 1 into, you can bring this denominator x square to numerator, that becomes x power minus 2 dx. Then so you can cancel out x here, minus it is 2y by x dy equal to 0. So let us take this as equation 1. So this is in the form some m1 dx plus n1 dy equal to 0. So here m1 is equal to some 1 plus y square plus 1 into x power minus 2, and n1 is equal to minus 2y by x. So definitely we'll get dou m1 by dou y is same as the dou n1 by dou x. In the previous class also I explained about the use of integrating factors to make the given differential equation becomes exact. So after multiplying the given differential equation, the equation 1 simplified to this form. So definitely this equation 1 becomes exact here. That is dou m1 by dou y and dou n1 by dou x for this differential equation. So definitely we'll get this as same. So once it is the differential equation is exact, then we know that the general solution is, the general solution will write it as integration sum m1 dx, because m becomes m1 and n becomes n1 here. So this is equal to c. So here in the first integral we take y as constant, in the second integral so we have to take the terms which do not contain x. Okay, so here if you observe n1 here, this integral, so in n1 it is containing x, only one term it is containing x, we don't want to take this term in the second integral. So finally we left with this integration 1 plus some y square plus 1 into x power minus 2 dx, plus here there is no term which do not contain x here, so that is 0 dy is equal to c here, right? Then finally, so coming to the solution, So integration of 1 into dx, no? So 1 plus 1 into dx, integration of 1 into dx, then so this is a constant, this is a constant, y square plus 1 is constant, integration of x power minus 2 dx we have to do here. So integration of 1 into dx is x plus 1 plus y square is anyway constant. In this integral we treat y terms as constant, no? So integration of x power minus 2 is minus 1 by x, so is equal to c here, right? So that implies we can write this as x square after taking x as LCM. So we can also write this as minus 1 plus y square, so is equal to or divided by x, this is equal to c here. That implies x square minus of 1 plus y square is equal to cx. Let us bring cx to this side. X square minus y square minus cx minus 1 equal to 0. So this is the required solution of the given non-exact differential equation by using method 3, right? So suppose if you see this expression 1 by n dou m by dou y minus dou n by dou x is not function of x, we will not apply this method. Sometimes we may get this as function of y, or maybe combination of x and y terms also. In those cases we cannot go to this method. Then we have to think about the alternate methods to find out the solution of this non-exact differential equation, right? Now I will explain how to find out the solution of the non-exact differential equation by using method 4. So coming to method 4, so we know that to check that expression, that is 1 by m, the difference dou n by dou x minus dou m by dou y is function of y or not. If that is the function of y, we will write integrating factors e to the power of integration g of y dy here. To explain this method, so let us take one more problem. So that is solve the differential equation y square plus 2y dx plus xy cube plus 2y power 4 minus 4x dy equal to 0. So this is a given differential equation. So this is in the form m dx plus n dy is equal to 0, where m is equal to y power 4 plus 2y, n is equal to xy cube plus 2y power 4 minus 4x. Let us verify the condition for exactness, that is dou m by dou y and dou n by dou x, whether they are same or not. So here dou m by dou y is 4, it is, so this value is 4y cube plus 2. The differentiation of m with respect to y is 4y cube plus 2, and differentiation of n partially with respect to x is y cube is constant into 1, x differentiation is into 1. So completely this is constant, the derivative is 0, minus 4 into x derivative is 1. So is equal to y cube minus 4. So here dou m by dou y is 4y cube plus 2, dou n by dou x is y cube minus 4 we got here. So therefore dou m by dou y not equal to dou n by dou x. Therefore the given differential equation is non-exact. Therefore the given differential equation is non-exact here. Coming to the solution of this differential equation, what we'll see here is whether that 1 by n into difference is function of x, or 1 by m into the difference is function of y or not. In the previous problem we got 1 by n into the difference is function of x. So this problem will see whether 1 by m dou n by dou x minus dou m by dou y, this difference is function of y or not. Let us check this. 1 by m, what is m here? So m here is, so 1 by y power 4 plus 2y. The difference between dou n by dou x and dou m by dou y here is, so that is dou m by dou y. So here this is 4y cube plus 2, and dou n by dou x is y cube minus 4. Let us write this y cube minus 4 minus 4y cube plus 2. So this is equal to 1 by y into y cube plus 2 here. So in the numerator we'll get this as minus 3y cube. So it is minus 6 we'll get. So by taking minus 3 outside, y cube plus 2 divided by y into y cube plus 2. So this is equal to minus 3 by y we got. So this is the function of y here. Okay, here we got 1 by m. This dou n by dou x minus dou m by dou y as minus 3 by y, that is function of y. If it is a function of y, then we'll take the integrating factor as e to the power of integration some g of y dy is equal to e to the power of, so what we got, function of y is minus 3 by y. So that is minus 3 by y dy is equal to e to the power of minus, this is 3 log y is equal to e to the power of log y to the power of minus 3 using, so this m log n formula. M log n is log n to the power of m. Again using the basic formula in logarithm, that is e to the power of some log m, base is m. Here m is y power minus 3. So you can write this as 1 by y cube. So therefore the integrating factor we got here is 1 by y cube. So let us multiply this integrating factor with the given differential equation. The differential equation here is y power 4 plus 2y plus xy cube plus 2y power 4 minus 4x into dy equal to 0. So let us multiply this integrating factor with the given differential equation. So our differential equation becomes y power 4 plus 2y by y cube into dx plus xy cube plus 2y power 4 minus 4x divided by y cube into dy equal to 0. So let us separate the terms here. Y power 4 by y cube is, so this is y plus 2y by y cube is 2y square into dx plus, so xy cube by y cube is x will get plus 2y power 4 by y cube is 2y will get minus this is 4x by y cube into dy equal to 0. So take this as equation 1. So this is in the form m1 dx plus n1 dy equal to 0. So definitely we'll get dou m1 by dou y is same as dou n1 by dou x. So this is the exact differential equation. One is exact now. One is exact differential equation here. So therefore the general solution will write here as, the general solution is, we know that it is integration m1 dx, that is y plus 2 by y square into dx plus integration n1 dy, the terms which do not contain x. It is having x first term and third term. So only 2y which is not having any x. So we have to take this term here. So that is 2y dy is equal to c here. So that implies, so completely this is constant. We will treat in the first integral y plus 2 by y square into integration of 1 into dx is x plus integration of 2y dy is y square is equal to c. So this is the required solution of the given non-exact differential equation using method 4. This way, by applying method 4, we can find out the solution of the non-exact differential equation. So this is about the finding the solutions of the non-exact differential equations using method 3 and method 4. In first class, I have explained about what is the exact differential equation. Then if the given differential equation is exact, then how to find its solution using this general formula, that is integration m dx plus n dy equal to c. So in the first integral, we will treat y as constant. In the second integral, so we have to take the terms which do not contain x. Okay, this point carefully you have to observe. In the second integral, we have to consider only the terms which do not contain x. But in the first integral, all the terms will keep y as constant in the first integral. Then if the differential equation is non-exact, that is dou m by dou y not equal to dou n by dou x, then we need to calculate the integrating factors here. There are many methods are there to find out the integrating factors. So method 1 tells that whenever the differential equation is non-exact and if it is homogeneous, then the integrating factor will write it as 1 by mx plus ny, provided mx plus ny not equal to 0. Method 2 tells that if the differential equation is non-exact and in the standard form y into fxy dx plus x into some other function of xy dv equal to 0, then integrating factor is 1 by mx minus ny. So where mx minus ny not equal to 0. So if it is not homogeneous and if it is not there in the standard form and if it is a non-exact differential equation, then we will go to the method 3 and method 4. So in method 3 what we'll see is this expression 1 by n dou m by dou y minus dou n by dou x is function of x. Then we'll take the integrating factor as e power integration f of x dx. In method 4 what we'll see is whether this 1 by m, this difference is function of y, integrating factor will take it as e power integration of g of y dy. To decide this method 3 or method 4, roughly we have to check these two conditions, whether 1 by n the difference is function of x or 1 by m the difference is function of y or not. So if any one of these conditions satisfied, then we apply the respective integrating factor formula here. So using those four methods, this class I have discussed about method 3 and method 4. So this problem we have tried using method 3. Then using method 3, how to find out the solution of the given this non-exact differential equation 1 by. Then after that using method 4 also, how to find out the solution of the given non-exact differential equation. Right, these are the two problems using method 3 and method 4. How to find its solution we have discussed. Then if you try some 1 or 2 problems, then you can understand these two methods clearly. So you can note down the homework problems here. That is, first one is solve the differential equation some y into xy plus e power x into dx minus e power x into dy equal to 0. So this is one problem. So based on that difference and that expression, you have to decide method 3 is applicable or method 4 is applicable. Then coming to the second one, solve the differential equation 3y square plus 4xy minus x into dx plus x into, it is x plus 2y into dy equal to 0. So these two problems you can try at home. If you want, I can give you the answers also. Coming to the first one, answer is x square by 2. The solution of this differential equation will get here as x square by 2 plus e power x by y is equal to c. If you want, you can note down integrating factor also. Integrating factor will get this as 1 by y square. And coming to the second problem, the solution of this second problem will get it as x cube y square plus x power 4y minus x power 4 by 4 is equal to c. And the integrating factor will get this problem as x square. These two problems you can try at home. Right, this is about method 3 and method 4 to find out the solutions of the non-exact differential equations. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.